Okay, the next question will also be based on the exercise. Okay, so in the exercise, okay, we have been given a question number 58 actually. So I will be doing the question number 58. Okay, and this question says that with reference to exercise 35, construct 98% confidence interval for the ratio of variances of two population sampled. Okay, and the other one says 59. It says the reference to exercise 36, construct 90% confidence interval for the ratio of the variances of the two population sampled. So we can do either of one, either 58 or 59. Okay, so let's see the data and do the complex one of it. Okay, okay, 35 says that, okay, 36 one, this 59 problem, this is I already solved it in the homework. So we will be doing the 58. Okay, we will not be doing the 59, we will do the 58 because I already solved it in the 59 is already solved. So let's do the 58 one, which says that construct 98% confidence interval for sigma 1 square by sigma 2 square based on the data from the two samples taken from the normal random populations. Okay, so it says that 20 randomly selected mature citrus trees of one variety actually have a mean height of 13.8 feet and standard deviation of 1.2 feet. So it says that 20 randomly selected, so it means that the sample size n1, okay, we have citrus trees, okay, this is the sample A, and it says that 20 randomly selected. Okay, so it means the sample size of the citrus trees is 20. Okay, and the mean height x1 bar is equal to 13.8 feet. Okay, and the standard deviation s1 for this sample is 1.2 feet. Okay, and the 15 and citrus trees B, actually this group, actually it says that 15 randomly selected mature citrus trees of another variety of, okay, so for variety B, the sample size n2 is equal to 15 citrus trees, and the average height that we found in this case is 12.9 feet, while the standard deviation for this sample is 1.5 feet. 1.5 feet. Okay, so we are going to construct a 98% confidence interval for the true population variances proportion. Okay, so we know that the true proportion confidence interval for sigma 1 square by sigma 2 square, actually it is equal to s1 square divided by s2 square into 1 divided by f of alpha by 2 and 1 minus 1 and 2 minus 1 separated by comma f of alpha by 2 and 2 minus 1 comma and 1 minus 1. Okay, so alpha is equal to 1 minus p, while p is equal to 98%, which is 0.98. So 1 minus 0.98 is equal to 0.02. This is the value of alpha. So alpha by 2 is equal to 0.02 divided by 2, it gives us a value of 0.01. So f of 0.01, so f of alpha by 2 and 1 minus 1 and 2 minus 1 is equal to f of 0.01 comma and 1 minus 1 is, and 1 is equal to 20, so 20 minus 1 comma and 2 minus 1 is 15 minus 1. So we get f of 0.01, 19 and 14. Okay, and f of alpha by 2 and 2 minus 1 comma and 1 minus 1 is equal to f of 0.01 and 2 minus 1 is 15 minus 1, so it is 14, and 1 minus 1 is 20 minus 1, which is 19. Okay, the roles will be reversed over here. Okay, so we need to find these values from the f table, f critical values table. Okay, and we are going to calculate the ratios of the sample variance, which is s1 divided by s2 square, actually s1 square divided by s2 square. Okay, we are going to calculate this thing from this data. Okay, so the first thing is we are going to calculate s1 square. Okay, so s1 square is equal to, s1 is 1.2, so 1.2 square, we must calculate it. So using calculator, actually we have 1.2 square is equal to 1.44. Okay, so let's put the values over here, and s2 square is equal to 1.5 square. Okay, so it gives us a value of 1.5 into 1.5, which is 2.25. Now we have these values, so the ratio is equal to s1 square divided by s2 square, and it is equal to 1.44 divided by 2.25. Okay, so let's calculate 1.44 divided by 1.44 divided by 2.25, which is equal to 0.64. Okay, this is s1 square divided by s2 square. Now we have the ratio. Okay, so what we need to calculate now is the tables, these values from the tables. Okay, specifically these twos. Okay, so let's calculate it. F of 0.01, 19, 14. Okay, we need to calculate this value, and for 0.01, 14 and 19. Okay, from the f critical table values. So let's open the critical values table and see where these ratios actually lies. Okay, so I want actually in the numerator first we have 19 and in denominator we have 14. Okay, so the denominator 14 is over here, but the numerator is up to 9. So in the next page the denominator will remain constant and this will change. Okay, now this don't have any 14 over here, it is on 15, and we need it for 19, but it doesn't have any 19, it has 20. So the nearest is 20. Okay, so we can find it for the 20 and 14. Let's see if I find any 19 over here in the, no, there is no 19 in the numerator. So Okay, let's see where the 14 is. This is first, second, third, fourth, fifth, sixth, and seventh. And in the seventh, we need to calculate this. Okay, this is 8, 9. So this is first, second, third, fourth, fifth, sixth, and seventh. And in the seventh, the fourth one. Okay, so go page down. Okay, this is first, second, third, fourth, fifth, sixth, and seventh. And in the seventh, we need to calculate the fourth one. Okay, this is the fourth one, 3.94. And we don't have 19 in the actually the numerator. So we have 20. 20 is the nearest, so we calculated for 20. Okay, 3.94 against this going up to 20. This is 3.51. Okay, so we have 3.51 value for the f of 0.01, 19, and 14. This is 3.51. I will also use web to confirm it. Okay, let's confirm it from web. Okay, or using scientific calculator, we can also find this value. So let's first confirm it from website that we get the, because we got it for the 20 and 14. We didn't get it for 19, we got it for 20 and 14. I hope that the ratio for the value for f of 0.01 20 14 is equal to f of 0.01 19 and 14. So let's see. Okay, using the web, actually the degree of freedom 1, it means the numerator. The numerator is 19 and the degree of freedom for denominator is 14, and the probability level is 0.01. Okay, so let's calculate and find out. Okay, so calculate and see what it gives us. Okay, so it gives us a value of 3.529, which is 3.53. Okay, and here we get 3.51. So not that different, but the actual value is 3.53. Okay, this is the value. And same, we will be using the same resource. Okay, let's switch the the degree of freedoms. Now the numerator is 14 and the denominator is 19, and let's calculate what it gives us. Okay, it gives us a value of 3.19, actually 3.195. Okay, so let's use this value, 3.195. this is 3.195. Okay, so now we have the ratios, and also we have the f values. So let's multiply with the respective and let's see. So the s1 by s2, s1 square divided by s2 square, actually it is equal to 0.64. Okay, so we know that s1 square divided by s2 square is equal to 0.64. Okay, and these are the f values. So 98% confidence interval for the true population variance proportion, it is equal to 0.64 multiplied by 1 divided by, okay, so this is the first one, and 1 minus 1 and 2 minus 1. So the first one is 19 and 14. Okay, f of 0.01 19 and 14. Okay, this one, so 1 divided by 3.53. okay, and f of 0.01 14, 19. This yields a value of 3 point, we can say 3.2, but let's use the 3.195. Okay, so it is 0.64 divided by 3.53 and 0.64 multiplied by 3.195. So the confidence interval is calculated as, the first value that we get is 0.64 divided by 3.53. okay, this is 0.1813. okay, and then 0.64 multiplied with 3.195, that gives a value of 2.0448. okay, so let's round it off. We get 0.18, okay, and 2.04. okay, these are the values up to 2 decimal points. okay, so these are the values that we get for the interval or range. okay, and one thing that you need to focus is to put the respective values over here. okay, you need to focus on which one value is here and which one value is here. That is very important thing. okay, don't miss it out. If in exam it is a question like, this comes, okay, maybe you are given the formula sheets for this. okay, but still you have to memorize, okay, that what is the exact formula. okay, so you need to put the respective value over here or here. You cannot miss this out. If you miss this out, you will get the absolute opposite range. okay, so that is the most important or critical thing to look for. Thank you. Okay, so in this video we will be doing the very last topic of the estimation, and this is the estimation of the ratio of two variances. It means that we will estimate the ratio of the two variances. okay, sigma 1 square by sigma 2 square. We will actually estimate this ratio. okay, and how it will be estimated? It will be estimated on the basis of, this will be estimated on the basis of sample variances of two samples, N1 and N2, from two independent populations following a normal, both are normal populations. okay, so we will take two samples from two populations for which we don't know the variances of the population of the variances are, the variances of the population are unknown, but we know the variances of the samples taken from two populations which are independent of each other and follow the normal distribution. okay, so this is the whole scenario, and based on that we will estimate the ratio of the real population variances. okay, so for this actually we can go to the theorem, and the theorem says that if theorem is, okay, this is the theorem that will be used regarding this, okay, and it says that if s1 square and s2 square, okay, these two are the variances of independent random samples of size n1 and n2 respectively, then the confidence interval for sigma 1 square and divided by sigma 2 square, okay, this is equal to s1 square divided by s2 square multiplied by, okay, 1 divided by f of alpha by 2 and 1 minus 1 comma and 2 minus 1, okay, this is the degree of freedom for both, comma f of alpha by 2 and 2 minus 1 into and 1 minus 1, okay. So if I can simplify this for you, I can simplify it as that the ratio of the sample variances multiplied by 1 over f of alpha by 2 and 1 minus 1 comma and 2 minus 1, okay, this is one side, okay, and the sigma 1 square is greater than this, sigma 1 square divided by sigma 2 square, the real ratio of the population variances, it is greater than this part and it is less than sigma s1 square divided by s2 square multiplied by f of alpha by 2 and 2 minus 1 comma and 1 minus 1, okay. So this is now the real confidence interval, okay, this is one side of the interval and this is the other side of the interval, okay. So we will use this formula specifically and we will find the ratios of the real population variances based on the given sample variances for two samples n1 and n2, which are taken from the normal populations, two normal independent populations, okay. So let's do a question or two on this, okay, and find out like how we can actually implement this in real life, okay, using some examples. So let's do example 1 on this. Okay, this example says that with reference to example 6, find 98% of confidence interval for sigma 1 square by sigma 2 square, okay. It says that find 98% confidence interval for sigma 1 square divided by sigma 2 square. We need to know the 98% surety for the range in which the ratio of the population variances actually falls, okay, and it is based on example 6. So let's switch to example 6 and get some data, okay. So the data that example 6 gives us is a study has been made to compare the nicotine content of 2 brands of cigarettes. Okay, 10 cigarettes of brand A. So it says that we have 2 brands A and brand B, okay, of cigarettes. So the number of cigarettes for brand A is 10. So and 1 is equal to 10 actually, okay, and it has an average nicotine content of 3.1 milligrams. Okay, so x1 bar is equal to 3.1 grams. Okay, and with a standard deviation of 0.5 milligram. Okay, and standard deviation of sample 1 is 0.5 mg. Okay, now let's get the data for the second brand. While 8 cigarettes of brand B. Okay, so N2 is equal to 8 cigarettes, 0.8. Okay, now sample size for N2 is 8, and it has 2.7 milligrams of 2.7 milligrams, and the standard deviation for sample 2 is equal to 0.7 milligrams. Okay, now we have in this whole scenario we need the standard deviation of both samples. So both sample standard deviation is given to us. Okay, alpha, as it is talking about 98% confidence interval, so as the p is equal to 98%, okay, alpha is equal to 1 minus p, so 1 minus 0.98 is equal to 0.02. okay, and alpha by 2 will be equal to 0.02 divided by 2. Okay, now we have the alpha by 2 value also, and 1 is given and 2 is given. So let's put the values into the mathematical formula, and let's see how we find the confidence interval. Okay, so 98% confidence interval for the variance ratio for a true population, it will be equal to s1 square divided by s2 square multiply by 1 over f alpha by 2 and 1 minus 1 and 2 minus 1. Okay, comma s1 square divided by s2 square into f of alpha by 2 and 2 minus 1 and 1 minus 1. Okay, so let's find out. So s1 square is equal to, we have the standard deviation is 0.5 milligrams, so 0.5 whole square, it will get us 0.25 milligram. S2 square is equal to 0.7 whole square, so it will get us 0.49 milligrams. Okay, now we have the values for s1 square and s2 square, and 1 is equal to 10 and then 2 is equal to 8. We also have these two values. Okay, so s1 square divided by s2 square, the ratio of the variances of samples is 0.25 divided by 0.49. So let's calculate it. That should give us 0.25 divided by 0.49. It is 0.510. Okay, Now we have the value for the ratios also. So putting the values into the equation, it gives us 0.510 multiplied by 1 over f of alpha by 2 is equal to 0.01. So f of 0.01 and 1 minus 1 is equal to 10 minus 1, and 2 minus 1 is equal to 8 minus 1. Okay, separated by comma, 0.510 multiplied by f of 0.01, and n2 minus 1 is equal to 8 minus 1, and n1 minus 1 is equal to 10 minus 1. Okay, so it will, this one actually it will be transformed into f of 0.0197. Okay, so we need to get the value from the f table. This one and this one will transform into f of 0.01, 7 and 9. Okay, these two are quite different values. Okay, because we have, this is the numerator degree of freedom, and this is the denominator degree of freedom. Degree of freedom for denominator. Okay, and this is the degree of freedom for numerator over here, and here the numerator is 9 and the denominator is 7. So it will give us different values. Don't be confused, you go, that these two are same. Okay, these can only be same if n1 is equal to n2. Okay, so you should be cautious when you are calculating this value. Okay, this is n1 minus 1, n1 minus 1 comma n2 minus 1, and this is n2 minus 1 comma n1 minus 1. Okay, this is the main thing that you should actually focus on when solving a question for the ratio of the two sample variances, okay, based on which you find the true population variances ratio. Okay, so let's move on to the next page and calculate this thing. Okay, so f of 0.0197 and f of 0.0179. Okay, let's find it out from the f table. Okay, so this is the f table. Okay, this is the degree of freedom of the numerator, and this is the degree of freedom for the denominator. Okay, so we need, the first one we need is f of 0.01, 7 and 9. Okay, so 7 is the numerator here, this is 7. Okay, and 9 is the numerator over here, so it will be on the next page. So let's find first the f of 0.0197. Okay, so this is 9. Okay, and this is 7. So you need to look up in the 9th column and in front of the 7 row. Okay, so the values over here, the values are these, but the probability that we are using alpha by 2 is equal to 0.01. So 0.01 is the fourth one. Okay, 0.010. Okay, so getting the value in front of 0.010. Okay, let me a bit take closer look of it. Okay, this is 0.010. Okay, and the value that we get over here is 6.72. Okay, so this is the value that we get. Okay, so the value that we get for f of 0.0197 is equal to 6.72. now we need to get the value for f of 0.0179. okay, from the same table. So the value of f of 0.0, so the value of f of 0.0179. Okay, now the numerator is 7 and the denominator is 9. Okay, this is the degree of freedom for denominator. Okay, and we want it for the probability level of 0.01. So this is 9 and in front of it is 0.01. So we need to look into the fourth row, okay, in the 9 segment, denominator of 9. Okay, so for 7 9 it should be this one. Okay, this is 7 9 and 0.01. So the value is 5.61. Okay, writing the value over here that we got. Okay, now the 98% confidence interval for the ratio of the variance of the population, it is equal to the ratio multiplied by, okay, we have the ratio multiplied by 1 over f of 0.0197. okay, so the ratio that we found was 0.510 actually. Yes, 0.510 multiplied by 1 by f of 0.0197. okay, 0.510 multiplied by 1 divided by f of 0.019 and 7. So comma 0.510 multiplied by the ratio directly. Okay, so it will give us 0.510 divided by 6.72 comma 0.510 multiplied by 5.61. So let's calculate this one and this one also to find the 99% confidence interval for the ratio of the variances of true population. So 0.510 divided by 6.72, it will be equal to 0.0759. so it will be 0.0759, so 0.76 actually equivalent to this thing. Okay, and 0.510 multiplied by 5.61, it gives us a value of 2.8611. okay, so this is the range where the ratio of the true population variances sigma 1 square divided by sigma 2 square actually falls. It will be somewhere, it is a 98% probability or chances that the true variance ratio is somewhere between 0.076 and 2.8611. okay, so this is how we find the ratio of the true population variances. Okay, I will do another example on it and then this chapter will be over. We will solve example the exercise question of 57 number question in the exercise. Okay, so it says that construct 98% confidence interval for the true ratio proportion of the population using the data from exercise question 34. So let's see what the exercise question 34 tells us. Okay, it says that a study of two kinds of photocopying equipment shows that 61 failures for the first kind of equipment took on average of 80.7 minutes to repair and standard deviation of 19.4 minutes. Okay, so we have two kind of photocopiers. Okay, so photocopier 1 and photocopier 2 actually over here. Okay, these are two kinds of photocopiers, and for the first one it says that a total of 61 failures were inspected. Okay, so the sample size n1 is equal to 61. Okay, and it says that the average time to repair the equipment for 80.7 minutes. Okay, so x1 bar to repair the equipment is 80.7 minutes, and the standard deviation for this sample was 19.4 minutes. 19.4 minutes. Okay, and for photocopier 2 it says that 61 failures of the second equipment took an average of 88.1. So n2 is also is equal to 61. Okay, and the time it took to repair was 88.1 minutes. Okay, with a standard deviation s2 is equal to 18.8 minutes. 18.8 minutes. Okay, now we have s1 which is equal to 19.4 minutes, and s2 is equal to 18.8 minutes. So s1 square is equal to 19.4 whole square, and s2 square is equal to 18.8 square. Okay, now s1 square by s2 square is equal to, because in the formula, okay, for confidence interval, and we want to form 98%, so for 98% alpha is equal to 1 minus p 1 minus 0.98 is equal to 0.02, and alpha by 2 is equal to 0.02 divided by 2, which is 0.01. Okay, so the formula actually is that 98% confidence interval for the real population variance ratio, it is equal to s1 square divided by s2 square multiplied by 1 over f of 0.01, actually, because alpha by 2 is 0.01, so f of 0.01 into n1 minus 1 and n2 minus 1 separated by comma into f of alpha by 2, which is 0.01, and n2 minus 1 comma n1 minus 1. This is very critical over here, you need to focus on it. Okay, these two are not same unless and until both the sample size are of equal size, which is same over here. Okay, 61 and 61. So we need to find this ratio s1 square divided by s2 square, which we are going to calculate over here, and we need to find the value from the table for this. So f of 0.01 and 1 minus 1 comma n2 minus 1 is equal to f of 0.01 and 1 minus 1 is equal to 61 minus 1, which is equal to 60, and n2 minus 1 is also 61 minus 1, which is equal to 60, and f of 0.01 and 2 minus 1 comma and 1 minus 1 is also the same, 60 and 60, so it will yield the same value actually. Okay, so now let's calculate these values from the table and also calculate this ratio. So s1 square actually is equal to 19.4 square, so let's calculate it. Okay, so 19.4 whole square is equal to 376.36. Okay, and S2 square is 18.8 square, which is 353.44. Okay, now we have got both the square values. Now the S1 square divided by S2 square, the ratio of the sample variances, it is equal to 376.36 divided by 353.44. So it gives us 1.0648, 1.0648, and it is equivalent to 1.065. Okay, so we will use this value as the ratio, and this value from the table, let's calculate it. Okay, let's open the table over here and find the okay, so this is the value for the 1, 2, 3, 4, 5 and 6. Okay, if we see the up page, this is for the 60. Okay, and for in the 60 we need to find the fourth one. Okay, in the fourth one, 60 denominator and fourth one, and this is the numerator. The numerator is up to 9. Okay, so in the next page this will remain same, but this will change. Okay, so it is first, second, third, fourth, fifth and sixth, and in the sixth we need to calculate the fourth one. So let's go page down. So it is first, second, third, fourth, fifth and sixth, and in the sixth we have the fourth one. Okay, and going in this direction towards 60, so it will give us 1.84. Here let me zoom it in. Okay, this will give us 1.84. Let me do it again. This is the page up. Okay, we have this thing over here. This is 60 for denominator, but in numerator we don't have 60 over here. The numerator 60 will be on the next page. This is the numerator 60. Okay, and the denominator is will be remain same. This is first, second, third, fourth, fifth and sixth, and in the sixth we have 0.10 on the fourth one. So going page down, so it is first, second, third, fourth, fifth and sixth, and in the sixth we have 1, 2, 3, 4. This is the fourth one, 2.60, that we need to find, and against this going to the numerator 60 actually, so it converges on 1.84. So the value of f 0.01 comma 60 is equal to 1.84. That is the value we were looking for. So it is 1.84. It will also yield the same value because numerator and denominator degree of freedom is same. Okay, now we have the values and ratios, so we can find the 98% confidence interval for sigma 1 square divided by sigma 2 square is equal to s1 square divided by s2 square, which is 1.065 multiplied by 1 divided by 1.84 comma 1.84. So doing the multiplication respectively, it gives us 1.065 divided by 1.84 comma 1.065 multiplied by 1.84. Okay, so let's calculate it. We get so the first value that we get is 0.578. Okay, and the second value that we will be getting is 1.065 multiplied by 1.84, which is 1.9594. so if I actually round it to the two decimals after the point, so it will give us 0.058, and this one is 1.96. okay, so this is the 98% confidence interval for the true population variances proportion or ratio. Okay, the ratio of the true population variances falls under 0.58 to 1.96, and the chances are that it falls in this one is 98%. So it is 98%. We are 98% confident that the true population variance proportion falls between this range. Okay, 0.58 to 1.96.